All right. So we're going to go over this lab on the ideal gas law. So we're doing this simulated lab where we go to this website and you can see we have this container where we can put a gas in it. So just put some gas in it. And you can see these molecules bouncing around and bouncing off the walls and each other. And apparently how this works is it actually, just has the molecules follow straight lines until they hit something, and they can actually simulate collisions. And we can study this gas, assuming it's kind of accurate in how it works. Now, a real gas, like if we have, say you have something like a balloon and you fill it up with gas, the number of molecules is enormous. It's, way beyond something we could simulate. There'd just be way too much to keep track of. And so this, I'm going to click on this tab here. It says width. So we can see like the width of this container is 10 nanometers. So we're dealing with an incredibly tiny container. And again, the number of molecules, you can see each one. It's a small, very countable number. So it's a little different than most of what we've been, like most of the real cases that we consider here. But it's a manageable problem. Okay, so what we can do, we can, like I said, there's two different types of gases. We have big molecules and we can have smaller molecules. These red ones are lighter gas. And you can see that, the lighter ones are moving faster, which is what we would expect. Basically, let me just bring up this. We know from, just thermodynamics that the average kinetic energy for any molecule is 3/2 kT. So it's the average for a molecule in a gas. And so it only depends on the temperature. It does not depend on what type of molecule it is. And so the smaller molecules have, the same energy that the bigger ones do, so they have to be moving faster. Now, we're just going to deal with one type. So what I'm going to do is open up this container, and you can see the temperature dropping and the pressure dropping now. We have gauges to record to read off the temperature and pressure. So I'm going to clear this out and just show we can also heat up the gas. So I'm holding this up. If you let it go, it drops down. So you can, just make small adjustments to temperature or just hold it and keep this. Now, I should point out, I could just clear the gas entirely, but, kind of fun to watch it go. So, and then we'll pump in more. We'll just deal with one type of gas for now. And, what we're going to do is we're going to study the ideal gas law in this simulation. We can get that last red molecule out of there. There it goes. And we can close the lid. Okay. So now one thing we can do is we can pause this. So like right now, we can actually count the number of molecules we have in our gas. Let's see what that's 8. Now, if we pump more gas in, theoretically we could pause it and count, but that's going to be a little more difficult. You have to keep track of which ones you counted. So an easier way, just to click this button. We can see there's 114 of those. And what we're going to do in like part 1 of this experiment, we're going to keep this number fixed. Now, what we can do, I'm going to bring down the temperature. This is 18 or almost 1900 Kelvin. That's extremely high. Let's cool this off to a more reasonable value. Pressure dropping. I'm going to get it down to like, something much less than room temperature. Let's look at a very cold gas to start with. Okay, so 185 Kelvin, that's pretty cold. You can see pressure's low. Molecules aren't moving around too much. So one thing to note is this pressure gauge. It's bouncing around quite a bit. Now, that's not something we'd normally expect from the behavior of gases. Like if you have a tire gauge or pressure gauge for the tire of your car, Yeah, you've got that little metal tube with that white stick that can move in or out depending on how much pressure it is. So it's like spring loaded. So if you apply pressure to it, it's going to be pushed outwards, but then the spring is going to compensate for that. So the more pressure, the more it's going to go outwards. The greater the pushing force. And again, if you hook that up to the tire of your car, you just read the steady value. It doesn't oscillate like this. And really, the pressure, that's the force on the container divided by the area of the container. That's not a constant thing in general, because if you look at some time interval, it depends on how many collisions there were in that time interval, and also how energetic those collisions were. The molecules are moving faster, it'll exert a greater force, so there's a lot of randomness involved. But in larger gases, we don't really notice this fluctuating pressure because it's based on statistics, it's randomness. And when you have a very large collection of molecules, if you have 1 mole of gas, you have 6 times 10 to the 23rd particles, the fluctuations are going to be too small to even be measured. And so this fluctuation we're seeing, that's just because we have a small number of particles. And it does make reading pressure a little complicated, but we'll talk about that soon, how we're going to do it, a practical way to read this. One thing, you could just watch it for a little while, see it fluctuate around, and just try to kind of estimate an average value based on that. Now, we saw we can open the lid. We can also change the volume. So here, expanded the volume up to a maximum of 15. We can also bring it down to a minimum of 5, or the width is 5 nanometers. So anywhere from 5 to 15. And let's look at here. We have a temperature of 185 Kelvin. What I'm going to do is I'm going to compress the gas. So we're doing work on the gas in order to compress it, and that we're putting energy into the gas, which would very often raise the temperature of the gas. But the way the simulation is designed, that's not happening. The temperature is remaining fixed. So what that means is there's heat escaping from the gas to compensate for the work that we're doing on it. So that's just the way that this is set up. So we're looking at an isothermal process. So we can compress a gas, do whatever we want to the volume of the container. Nothing's going to happen to the temperature. Pressure is going to go up and down. And so the first part of this experiment, we're going to do 3 trials. And we're going to keep the number of particles fixed at 114 for all 3 trials. So we're just going to do that. And what we're going to do is look at how the pressure and volume are related. Now we know we have the ideal gas law. So I'm going to get rid of this. Just from the ideal gas law, we know pressure times volume. Now I'm going to use this version of the ideal gas law. I'll write down this version. Because N is, this capital N is the number of particles, where a lowercase n would be the number of moles, but the number of moles is going to be an incredibly tiny number because we only have 100 or so particles. So capital N is the way to go here. Now there's a bit of a problem here, because if you look at this simulation, this is a 2-dimensional gas. It's just moving in, say, the XY direction. And so this isn't going to behave exactly like a real gas would in 3 dimensions. So what we're going to do is we're going to kind of write down our own ideal gas law for this. So I'm going to write it out. Basically, I'm going to start out by replacing K, which is Boltzmann's constant. We should expect a somewhat different constant here. We can't expect this to obey the normal ideal gas law because it's 2-dimensional. And so we have to come up with our own constant for this 2-dimensional gas. And being extremely creative, I went with the letter A, first letter of the alphabet. Yeah, kind of try to think what can we use for our constant here. Let's just call it A. I want to make one more change here. Let's go back to our simulation. And we can change the width of the container, but not its height. We're not even told what the height is. I think it's 10, but I don't know for sure. It kind of looks, if we set this, it starts out 10 nanometers wide, and it looks square, so I'm assuming the height is 10 nanometers, but we don't need to know that. So we can replace our volume with an area. I'll bring this back. But I want to replace our volume with just the width, because that's our variable. So our version of the ideal gas law for this two-dimensional gas with a fixed height but a variable width, we should expect this result is going to hold up. The pressure times the width is equal to the number of particles times this constant A times the absolute temperature measured in Kelvin. Yeah, let's go back to the simulation for a moment. The pressure gauge is measured in atmospheres. You can also look at it in kilopascals. Now I want to pause this for a moment. If you look at the number, you have 83841. Forget about the decimal point for a minute. They're very close to each other. And that's because the conversion factor between atmospheres and pascals, it's 1.01 times 10 to the fifth power. And so there's not going to be much of a difference in those numbers. I'm just going to stick with atmospheres because we've got nice, the numbers are a very reasonable size here. So I'm going to measure pressure in atmospheres. Temperature, you could do degrees Celsius if you want, but let's stick to Kelvin. So what we're going to do, we're going to keep the number of particles fixed. And we're going to keep the temperature fixed for a particular trial. So let's look at this. We've got a spreadsheet here. I'm going to just fill this out and then talk about this. Center everything. Oh, by the way, what I'm using for a spreadsheet is, you can see here, LibreOffice Calc. So that's, there's this thing called OpenOffice, which has kind of like a free version of Microsoft Word. And I actually prefer this to Microsoft Word. I mean, I think your students, you get Office to use for free. It's part of being a student. I could use it as well as a teacher, but I just don't like it. So I use OpenOffice for everything. So you can use this if you want. You can use Excel. They pretty much work the same. There's also Google Docs, which I think you can work with anything. You can work with Mac as well. So like there's all sorts of different spreadsheets. If you know how to work with one, hopefully you can work with another. And if there's any little thing that you're hung up on, a good way to figure that out, well, you can always ask me. I'm not sure I'll know the answer with all the different things out there. But you can always ask me in class if you get stuck on any technical issues like this. But another thing you could do, a really great source, just go to YouTube and type in the question that you're looking for, and there'll probably be like a 2 or 3 minute video showing you how to do that. So, I mentioned we're going to get back to our experiment that we're going to simulate. We're going to do 3 trials at different temperatures. And what we're going to do is vary the width and record the pressure. So the width goes from 5 to 15 nanometers. So let's just go 1 nanometer increments. So I'm not putting units here. We're just collecting the data. I also want to put some more information here. The number of particles and the temperature. The number of particles that we're dealing with, that's going to remain fixed for the entire experiment. That's 114 for me. You'll have a different number. But so I'm going to write this 114 for all 3 trials. And the temperature we have now for trial 1 is 185 Kelvin. We'll change it for the other trials. I think I'll just do 2 because we're really, you'll do this experiment with 3 trials, but I think just doing 2 that'll be enough information where doing a third won't substantially change anything. But I have to do 2 trials to show one part, like the graphing part, what we're going to do. We get started. Now, we want to record data from the experiment. So what I'm going to do, I'm going to write down, I'm just going to make this table, the width and pressure, and just do this on paper. And then transfer it over the spreadsheet, so we don't have to keep switching back and forth between them. So I'm just writing this down on paper. The 5 to 15, and then the pressures. I'll write those down on paper, and then it'll be quicker to just switch over. So let's actually take some measurements. So we're going to start at 5. Okay, now again, we've got this gas moving around. The pressure is fluctuating, which can make it difficult to read. But we can just do this. Let's pause it. So right now for 5, I'm going to write down 16.9. Now, again, this isn't perfect because, again, if I pause it again at some random moment, now we have 16.6. So again, there's going to be some errors in our measurement, which, is something to talk about in the error analysis section. So again, maybe it would be a little more accurate if you took several measurements at a given pressure or a given volume. Yeah, we could do like, say, 16.9, 16.6, and 16.1. Just like randomly pause it 3 times and then take the average of those. So you could do that if you wanted to. But I'm just going to stick with, there can be a substantial difference. The number I recorded is 16.9, here's 16.1. So maybe it'd be better to do it that way, but it actually works out. I actually recorded an entire lecture explaining this, but I was using a different screen record, and when I brought up a different screen, I didn't realize until I reviewed it afterwards that it was only showing the website the entire time. So these other screens I was bringing up and talking about, you couldn't see those, so I have to redo this. But, the numbers actually worked out fairly well just by taking this snapshot. So it would be more accurate to take an average for each measurement. But this actually does work, so we can kind of just go with this. I'm going to go up to 8 nanometers, that'd be 10.2. All right, so while I'm taking this measurement, I guess I could talk about what we're going to be doing with this kind of data that we're collecting. And we're going to do 2 things. One, we have an isothermal process. So we want to see what that's going to look like on a PV diagram. We know what it's supposed to look like, so we'll see what our data says. So that's one thing. And also, just real quickly, I want to go back to this. This is our version of the ideal gas law for this experiment. We also want to find that constant A. So we're going to do 2 things. So we'll start by just collecting the data. We have 14, so that's 5.4. Okay. And 15. Oh, so you notice that didn't change. So that's going to look a little strange on the diagram. But again, it worked out fairly well. Okay. So that's one set of data for this particular temperature, 185 Kelvin. And I'm going to now change the temperature and get another set of measurements before going to the spreadsheet. So I'm going to heat up the gas. Let's say 377 Kelvin. Okay, so I'm writing that number down so I can put that in the spreadsheet as well. And then we'll go through and do the same thing. And again, in the actual lab, you'll do this 3 times. But for just this video, so I'm going to pause it to make things easier and just start recording these values. Yeah, I think it's better just to get all the data at once and then transfer it to the spreadsheet. Minimize moving things around. Okay, so I've got all the data for 2 trials. So I'm going to bring up the spreadsheet and just fill in these numbers. I'm also going to put this new temperature in. We had 377 Kelvin there. Okay, so I've got data. I'm actually going to delete this column because I'm not using it. So the first thing we want to do is plot this data, like make an actual PV diagram. And we want to have both, or in your case, all 3 curves on the same graph. So what I'm going to do is I'm going to highlight the data, and only the data, not the labels, like the W, P1, P2, and number and temperature. So I just want to highlight the actual data. And then I'm going to go to Insert Chart and go to XY Scatter. I'm just going to hit Finish. So here's our data. Now, I don't like the way this graph looks, to be honest. So what I'm going to do is I'm going to click on these. I'm going to select this data. So I clicked on this data set. And then I'm going to right click on one of these data points and say Format. And I'm going to change the shape to make it more circular. This looks kind of circular here. And I changed the size to be much smaller. So now if we look at it, it looks just like data points. I just prefer to how it looks that way. Okay, and then same thing for this data set. So I'm going to pick this circular looking symbol and okay. So we've got our 2 data sets. And something we definitely want to do is label our graph. So again, I highlighted the graph itself, and I'm going to right click, and that's not going to help. So let's see, how do we do it? Okay. So I think I initially highlighted the wrong thing. Like this chart is a lot of different elements, and sometimes it can be hard to select what you're actually looking for. So what I'm going to do, insert titles. So let's start with the x-axis. That would be the width in nanometers. And for the y-axis, we have the pressure in atmospheres. And you can also do it this way. You could just do width and then nanometers. And, pressure, put the units on the secondary axis. But let's go with this. Now, the title itself, what I'm going to do is I'm going to call this Figure 1. And we need a name for the title. And the easiest thing to do, but also something completely pointless to do, is just to call this like pressure versus width. And the reason why that's pointless is because you can tell from looking at the axes that that's what it is. So it doesn't really give us any information we don't already know. So what I'm going to do is call this isothermal expansion of a gas. And I'm also going to include this. N equals 114, just so we know like how many particles there are. And then click OK. So you just want to give like a name to your graph and definitely label the axes and include units. Now, another thing I'd like to do, let me come back to the screen for a moment. So here's our equation, and our variables are pressure and width. So like basically, there's our variables. And N is constant, that's 114, that's just a number. A is some unknown constant, and for any data set, the temperature is constant. So basically, what we have, mathematically, this equation we have is just like y is equal to some constant over x. Because pressure is on the y-axis, width is on the x-axis, and so if we just solve for y, we have, this is a hyperbola. We know exactly what this shape is. Oh, we could also write this as some constant times x to the minus 1. So I want to go back and going back to the spreadsheet, I'm going to select this data again. By clicking a data point, you can see like all the data is selected. It might be different depending on what spreadsheet you're using. And right click and say insert trend line. And the type, I'm going to pick power. This power is basically the like y equals x to the n. And so we have like x to the negative 1, multiplied by some constant. So this should give us a pretty good, it should be able to figure out the exponent 1 will give us a good fit. And it works. So here's our data. Actually, I'm going to undo that. Okay, I don't want to undo all that. That was weird. Okay. But I do want to fix it. Something here. So again, it can be hard to select. Okay, so here's the trend line. I'm going to format that and give it a name. And I'm going to call this 377K. So before we had like the trend line, it was given this key, column C, which, who cares? You're going to look at the graph. You're not going to see like that this was column C in the spreadsheet. And then change it back for some reason. So I'm going to select the data again. I think maybe, and then click OK. Why did it keep going back? I'm not sure what it's doing here. Okay. Okay. Hopefully that worked. I didn't want to do that. So I'm going to insert a trend line for this one as well. And again, I'm not going to forget this time. This was at a temperature of 185K and power. Okay. And it did it again. Click OK. Okay, so now it's looking good. Hopefully it won't do what it did again. I can save it. Just do that. Okay. Yeah, it keeps going backwards. An issue here. But anyways, that's the idea. We'll have these two trend lines. I'll give another try to... Yeah, it keeps going back for some reason. Okay, there, now it's looking good, and now it's not. So this is a glitch. I've never had this. Okay, so now it looks good. And actually, we're done with this graph. So what I'm going to do is I'm going to save it. So something nice. I don't know if I know Microsoft has this kind of a standard thing, a snipping tool. We can just take a screenshot of this, and I'll just save it now. Save. Let's call this figure 1. Okay, so now it looks good. Now, one thing I don't like, and I'm trying to figure out, I tried last time I recorded this to figure out, like, how to get rid of column B and column C. I don't want that. But again, now, there's one way to do that. There's got to be a better way to do this. But I'm going to open this picture with Paint and just delete it myself. So here I can just, delete this stuff. There's got to be a better way to have the computer not display it at all. But I kind of want to just move this down a little bit. Okay, so now it's basically looking how I like it. So again, we can see you'll have 3 curves, but just looking at the data, the blue one is 185 Kelvin. The red one is 377 Kelvin. It's got these squares, which I should have gotten rid of. But again, yeah, I could redo it. I'm going to leave it as it is. So it's having some weird glitch I never saw before. But I've got a graph, and that's figure 1. Okay, so that's one thing we want to do, is create this PV graph. Now, another thing that we want to do is we want to find this constant A. So let me clear this up a little bit. Now, there's a couple ways we could find this constant A. One would be what we've already done, but we have this power law. I think it'll be better if we linearize the data. So, yeah, like these graphs. Okay, I don't like this graph because it keeps reverting back to this previous state for some reason. But I already saved it, so I have it. I can always bring that back. But the idea is we want to linearize the data. And what I'm going to do is here, I'm going to write down slope. Just we're going to need that. So, yeah, let's go back to the equation. So, this is something I know students sometimes struggle with initially. I had in 121, I usually have an entire lab just on this process of linearizing data. And that was like one of the most difficult labs. Like after grading it, some students didn't quite get it. So I'm just going to, like normally I would kind of give this to you, linearize the data and you figure it out. But I'm going to just show you, walk through the entire process. And then in future labs, hopefully this will make sense. So anyways, the first thing we want to do is we've got 5 variables here. But you have to look at like what we're plotting is a PV diagram. Or a PW diagram. Pressure and width. Okay. And so our data, like we're going to make x equals, in order to linearize it, we need to change the variables. X equals and y equals. And y is equal to p. That one, let's just go straight with that. But if we let x equals w, we're going to get this hyperbola again. So in order to linearize the data, let's do this. Y is equal to p. So let's write it like this. P equals N A T divided by W. So now we have it like Y equals something. And remember that N, A, and T are constant. So we have some constant times our variable, which is 1 over W. So what we're going to do is we're going to let X equal 1 over W. So what we're going to plot is P as a function of 1 over W. And then let's look at this substitution. Y equals t. So we have y equals, and then we have NAT times 1 over W with it, which is x. And I'm going to do one more thing. I'm going to say plus 0. And the reason for that is, our basic equation for a line is y equals mx plus b. So what we have here, if we make this change of variables, we've linearized our data where our slope is NAT and our intercept is 0. So if we plot our data with these change of variable, their data should fall in a line, and we can get a best fit line and get the slope and intercept. And our intercept should be somewhere around 0. And if we know the slope, then we can solve for A, because we know N and we know T. So basically what we're going to do is we're going to say A, which is what we're trying to find. That's going to be our slope, which we get from our best fit line, divided by NT. So ultimately, this is our goal. And we're going to do this for each set of data. So let's go back to our spreadsheet. And on the X scale, again, let's look at our graph one more time. So our X data is going to be 1 over W. So here I'm going to make a new column, 1 over W. But the rest of it's going to be the same. Like the P is just, or the Y scale, we just have, pressure. So what I'm going to do, we can just copy and paste the pressure. But for the 1 over W, we can always calculate that. Like for W is 5, we could do 1 over 5 and get 0.2. But what I'm going to do is I'm going to say equals 1 divided by, and highlight that cell. And the advantage of doing it this way is a computer, this is one of those rare cases where the computer is actually smart about these things. It does a lot of autocorrect things, which are usually more annoying than helpful. But here, like the cell is 1 over A2. If I just click this right corner and drag it down, you can see like this is 1 over A2. The next thing we'd want to do for 6, we'd want 1 over 6 or 1 over A3. It just automatically does that. And so it kind of saves time that way. Now we have 1 over W as a function of pressure. And just if you don't want it to do that, like say you want 1 over A2 for all of these columns, you could do that by putting these dollar signs there. So I'll just do that real quickly. And then it's going to divide everything by, this cell. You're telling it A2. Another thing you could do is you could fix column A but leave 2 variable. If we do that, I'm going to delete this dollar sign. And this should work then. This should give us exactly what we had before. So what this is doing is it's fixing column A, but as we drag down these cells, it's going to update. It'll change the row value to correspond to, what we actually want. Now again, if we drag this one sideways, it would keep this column A constant, but it would do like then 1 over 16.9 and then 1 over 33.3. So, that dollar sign by the A, you can take it or leave it. Doesn't matter. Anyways, now we're going to linearize this data. I also want to copy all this stuff over. And that did not work, so let's try again. Okay. So I'm going to highlight just the data itself and do what we did before. Insert chart, XY scatter, and just click finish. Now we have 2 lines. And I want to go through this same process. Now, again, when you have color, that's really nice because, you can see very clearly. One thing it does take different, one reason why it makes these icons so big is because that way you can see that this is like a diamond shape. This is a square. So if you saw this in the same color, you could distinguish them. But since everything is online here, it'll be easy to, just keep it in color. So we're going to do that. Format, I think it was data series, and change these icons. Yeah, I don't know if you could even notice visually, but just make these, and I always forget to do this, so I'm going to start over. Okay, so, oh no, I think that was fine how it was. It's that other part I always forget. Okay, so let's click OK. Now let's do the same here. And again, this is all appearance stuff, but that is important as well. So let's do that. Okay, so now we have actual data points. And of course, very important. Let's insert titles. Now this one, we're plotting the same data just in a different way. So I'm actually going to give this the same name for the subtitle. I think what we had before was isothermal expansion. With this, that number of particles. But again, it does have a different, we can't name it the exact same thing, but one's figure 1, one is figure 2. It's always important to include those, like figure 1 and figure 2. So if you're writing a lab report, you can say resort, or refer to figure 2, for instance, and then I know where to look for it. Now, our x-axis, this is 1 over width. And the units are 1 over nanometers. So it doesn't look right, but that's what it is. And again, pressure in atmospheres, and let's click OK. So now we have our graph, but a very important thing from here, we want to insert these trend lines. We want to put a best fit line in. So I'm going to select these data points and right click and say insert trend line. And this is the part I always forget. I'm going to put 377 Kelvin here, just so I don't forget. We want a linear. And what I'm going to do is say show equation. Okay. Now we have this really kind of messy looking equation. But what I'm going to do, this was for the red data set. That was 377 Kelvin. All I really care about is the slope. And again, I'm including 5 significant figures, which is way more than we need. Because remember, we have some significant errors in the data itself. If we did the experiment over again, we get different numbers because the pressure fluctuates. So having 5 significant figures is kind of ridiculous, but, I'm going to include that. Maybe we should just have 3. Yeah, maybe we'll just have 3. Okay, a little more realistic. And note that I'm not putting units anywhere. These are just numbers. We're just collecting data. Okay, now let's just look at the intercept, 0.2. Remember, the intercept was supposed to be 0. But it's not going to be a perfect 0 because we're fitting data which has errors. So if we had perfect data, the intercept would be 0. But just kind of as a check, 0.2, not that big. Especially on the scale we're looking at. On this vertical scale, it goes up to 35 roughly. So 0.2, yeah, that's a pretty reasonable number. Okay, now that I have that, I'm going to delete the actual equation. So I had to say show equation just so we could get the slope, but I don't want it on the graph because it looks kind of stupid with all those figures. So I'm going to do the same thing with this one. Insert trend line. This was at a temperature of 185 Kelvin. And we want it linear, and let's show the equation. Another thing, I'm going to do it here, and then not worry about it. Maybe I should have done that before as well. Yeah, for yours, do this as well. Show the coefficient of determination, r squared. We'll talk about that in a minute. So I'm going to move this over. So what we're going to do is write down the slope, 84.3. Check the intercept, 0.31, again reasonable. And I'm also going to record r squared. I'm going to put it somewhere else. I'll just put it here. R squared, 0.995. Okay. Now, what is R squared? Basically, it's a measure of how linear your data is. So according to our theory, our data should be linear, and if that was the case, then R squared would be equal to 1. So the better your data is, the closer you're going to get to 1. Now, I think what's interesting about these spreadsheets, I'm going to write down this number, 13.4. I don't really need to because we have this data over here. Yeah, I didn't need to write that down, actually. But I'm going to change this to 1,000. And the graph totally changed because I was in enormous. So what happened, what's really nice, in a way, is that when you change, yeah, I made the pressure up to 1,000. So there's a data point, way up over here. I don't know if we'll be able to see it or not, but yeah, when you change your data, the graph actually updates. Okay, so there's a data point all the way up here, which totally throws off our graph. And now if you look at R squared, it's 0.18, which is very far from linear. And that's because this one data point was so far off that it completely screwed everything up. So I'm going to fix that. Again, I can just do that to fix it. And then it brings us back to the values we had before. Or does it? Did I think I changed this number somehow. I made it 1,000. Oh, okay. Yeah, I screwed up just trying to fix it. Yeah, I just copied and pasted the data over. There's another way we could have done that where... Okay, so yeah, now we're back to the numbers we had before. 84.3 and R squared is 0.995. Now, again, I didn't do that for this first one. Like maybe could, but it's going to be about the same. This data, you can just tell from looking at it that it's basically linear. But again, put R squared value for, at least somewhere in there. You can do that for just like one set of data if you like. That's fine. Because, they're all going to be the same, basically. Like 0.99 something, very close to 1. Now, in the real world, things aren't always going to work out so nicely. And you can determine based on like your actual value of R squared, whether or not your assumption that the data is linear is valid. Like how assumption that, or how valid that assumption was. But again, for this experiment, because it's a simulation, and we're eliminating most of the experimental errors by doing a simulation. So it's not surprising that we get R squared close to 1. And again, you'll have 3 things for your lab. You'll have 3 lines. And so now that we have our slope, I'm going to make another column here called A, which is that constant that we're looking for. So here's our constant. Like our graph, A is equal to the slope over NT. So for starters, A is equal to our slope over NT. So let's just do this. Slope divided by, and I'm going to put parentheses, N times T. And this is kind of just like a starting value for A. We're going to have to fix that, and I'll explain why. But and we want to do the same thing over here. We could type the formula in, but the numbers are all in the same column that we're using. Like here, we have this number divided by the product of these two. And so if we just drag this over, it's going to do it automatically for us. It'll take this number, which is this is G15. So here it says G15. What we typed over here was F15, but because we dragged it over one column, it switched that F to a G. So it's kind of smart about doing that. Okay, so then we can do that for all 3 of our sets of data, and you notice that the values are very, very close. We have 0, 0, we have 3997. Here we have 3908. So like the first two significant figures, you know, it's we're basically getting very consistent results. So our data looks good. We have nice lines. I'll bring up the other one real quickly. This was our actual data. Again, this kind of behaves like you'd expect it to. We know it's, as the width increases, the pressure is going to drop. The data fits that line very well. And these look linear. So again, we're getting the same A, roughly the same A for both. And you'll have three values. And so like your final result for A, our accepted value for A would be just the average. So again, I'll just do that here. And what you can do is say average, type equals average, and then parentheses, and just highlight the cells you want to take an average of, and hit enter. So this would be my experimental result for A, 0.003953, except we're not quite done. We're missing one major thing. First off, just one thing I want to do, just to do it. I'm going to take a screenshot of this as well, just so I have it. So here's figure 2. I'm going to save that as figure 2. And again, you don't have to do this, but and there's probably a better way to do it. But I really don't like these column F and G because there is no, you're not seeing a column F or G. Like in the lab report, you're never going to see a spreadsheet. So it's better to get rid of that. And I'm sure there's a way to tell the computer not to display it at all. But I wasted some time trying to figure that out, and it didn't quite work. So I've got both figures saved. And again, that's always an option. Just take a screenshot. Various ways you can do that. This snippet tool is really nice. Okay, so I'm going to delete this figure now because, well, I'll leave it up for a moment. So what are we missing? We're missing one major thing. We want this constant A, but we have a number. We also need a unit. So let's go back to here. So remember, our pressure is measured in atmospheres. And W, 1 over W, the units would be 1 over nanometers. And so let's look at our slope. Now I'm going to clear up some room here. Let's get rid of that as well. So let's start here. So our slope has units of atmospheres divided by inverse nanometers, or atmospheres times nanometers. So if you multiply top and bottom by a nanometer, you have 1 over a nanometer times a nanometer. They just cancel. So our slope has units of atmospheres times nanometers. So if we look at A, let's look at the units for A. We have our slope, which is atmospheres times nanometers. And then we're dividing by N, which is just a number with no units. And then we divide by T, which is in Kelvin. So A has units of atmospheres times nanometers over Kelvin. And I want to get this in more SI units. So the first thing I want to do is convert it. And we know 1 atmosphere is 1.01 times 10 to the 5th power pascals. And a pascal is a Newton per meter squared, which I'm actually going to write as a meter times a meter. So again, that's a conversion factor. And we also know that 1 meter is 10 to the 9th nanometers. So let's kind of cancel some things out. Here we can cancel out one of these meters. Here we can cancel out nanometers. So if we multiply by these conversion factors, we have Newton. The units are going to be newtons. Oh yeah, the atmospheres cancel out as well. So what we're left with on top is just newtons. On the bottom, we have meters times Kelvin. So those are going to be the SI units for our constant A. Newtons over meters, kelvins. So when I ask for A in the lab report, I want it in these units because those are like the basic SI units. Now, one more thing I want to do is let's compare this to Boltzmann's constant. So the units for Boltzmann's constant are joules over Kelvin. And a joule we can write as a Newton times a meter over a Kelvin. So we're getting different units. And that's basically, we should expect that. And like here for Boltzmann's constant, we have a Newton times a meter over a Kelvin. And here we have a Newton divided by a meter. So basically the meter goes from the top to the bottom. Now, why is that the case? Remember, Boltzmann's constant is based on a three-dimensional gas, where our volume is in meters cubed. Where for our purposes, so that should be a 3. So yeah, volume in meters cubed. Where in our case, we have width, which is in meters squared. Or sorry, just in meters. So to convert a volume to a width, we'd have to divide by meters squared. And if we divide Boltzmann's constant by a square meter, we'd end up with these units, Newton over meters times Kelvin. So those are the correct units for A. So that's what we're going to do. So again, just this, getting used to how this simulation works. And also, if you're not very familiar with spreadsheets and making graphs, they kind of went over a lot of material on this lab because this is, might be some new things that we haven't done before in this class. So, and then another thing we could do all sorts of experiments with the simulation. Another thing we could do is change like the number of particles. And something kind of fun, let's put some new particles in there as well. Like the different types of gases. And notice it takes a while for them to spread around until they're uniformly distributed. Because they're entering the chamber on one side. And again, this is diffusion. They've got to work their way over to, they're uniformly spread around. So that'll take some time. And just for fun, let's heat it up and watch the pressure go. And eventually, in any real scenario, well, there you go. If you heat up the container too much, something's got to give. It can only handle so much. And so, now the gas is escaping, pressure and temperature are falling. We can put the lid back on, and now we have our gas contained again. So again, we could do this. We could, another thing we could do is here, this isn't as fun, but, you could kind of clear the tube and start over. There's a way you can just reset everything. But, another thing we could do is we could do an experiment like in that first experiment. We did, we fixed a number of particles and did 3 different trials. Where at different temperatures, something else we could do is we could fix a temperature and do multiple trials with a different number of particles. We could also mix the gas, like we have both types of molecules. So there's all sorts of things we can do with these simulations. But I think at this point, you should have a pretty good idea of how the simulation works. And then, I'm going to have written instructions about what we're actually going to do for the lab. So the first part, you don't really need written instructions because you have, we've gone over pretty much the whole procedure. One more thing I want to talk about, actually, on the spreadsheet, like we're also going to have a lab report. So I've got this just document here. One thing you could do if you don't like the idea of taking screenshots, I'm going to click on this graph and just do copy and paste. So you can get this into like a Word document or some other, I'm using an open office version of that. You also want to have data tables. So again, going to the spreadsheet, you want to have this information in your lab report as well. So what I'm going to do is I'm going to highlight this one and copy and paste that over here. Okay, so again, you can get this over here. This does not look very good. I'm going to make it bigger. You could do like a 2-column format type of thing. Here, actually, what I'm going to do is space these out. Okay, so a couple of things about this graph. One, we need description. Well, here we have 1 over W. We also need units, which I didn't write down in the spreadsheet because that's just working with numbers. Here we have pressure 1 in atmospheres, pressure 2 in atmospheres. And one thing you can do in a document that you can't really do in a spreadsheet, you're going to make these 1 and 2 subscripts. Okay, now this kind of data is totally unacceptable because it has way too many significant figures. So you'd want to change these. Like I'm going to call this 0.17. Just rounding off, and this will be 0.14. So again, this will be 0.13. There might be a way to have the computer round everything off for you, but I'm not going to bother with that. Yeah, we want the same number of digits. Here, 0.9. Well, so yeah, you don't want to include, this is actual data. You never want to have that many significant figures. I should have kept okay. Yeah, there's another number here. I forgot what that was, but that's fine. Okay, so you want to make sure you have the right number of significant figures for your data. Again, having 3 significant figures for the pressure, that's a bit much, but we'll just go with that. And again, because we saw it fluctuate, so I'm definitely not confident that P1 was 16.9. If you paused it, or if you let the simulation run and then paused it again, you almost definitely see a different number there. So again, 3 significant figures is definitely a stretch. So we should probably round those off to 2. But I'm going to leave them there and then just say that the, just kind of mention in errors that I'm going to fix this as well. I kind of give some idea of how many significant figures we'd actually have. So yeah, I'll give these 3 significant figures as well. Maybe we should give it 2. A little more accurate. So our value for A, and again, we're going to have to change these numbers because this has the wrong units, but it's not too hard to convert. We kind of covered that. Now, one thing you can see, this looked like maybe the table's okay here, but if you were to create a PDF, then this would not look okay because these gray lines are just for so you can see them, but they would not show up in the final document. So what I'm going to do is highlight this. Different ways of doing it. I could right click it or click, no, not that one. Here, this is borders. And just fill in these borders. Now, there's one thing missing from this table. This would be table 2. And kind of a description of, we'll call it linearized data for isothermal expansion. So all of your data tables should have label table 1, table 2. So table 1 would just be the raw data before, where we just have W instead of 1 over W. And then we'll also have a table 3, which I'll include. Yeah, I'll leave this down here. Here, let's put table 3 up here. We'll call this ideal gas law constant. So you're gonna have 3 values. Like here I just have 2. 0.0040, 0.0039. And again, those numbers would have to change. Oh yeah, so here we should have units on this as well. Here we're gonna have temperature. So my slope here would be atmospheres over Kelvin. So you want to change your units and the numbers with these conversion factors to make it Newton over meters times Kelvin. But, oh no, sorry, I screwed that up. The slope was atmospheres times nanometers. And I'm going to put a special character. I'm just going to put a dot in there. That's supposed to be there when you're multiplying units. It was A. The units for A were that was Newton over meters times Kelvin. And I'll put that dot as well. Okay. And so now for our table, we'll have 4 values. So I'm going to insert a table. I'm going to have 4 columns and 2 rows. And I'm going to put a border around it. So what we have is we'll have A1, A2, and A3, and A average. I'll just say AVG for average. And I'm going to make those subscripts everywhere. These labels, so like A1, A2, and A3 are going to be subscripts. And I'm going to center this. Now, we always want units, so I'm going to put them here. So units for A, actually, I'll just copy and paste this. And copy and paste the whole unit thing. And yeah, that'll have units as well. And then you put down like A1. Again, I'm not going to copy this. Well, yeah, I will. Here, I'll copy. Again, these numbers will be different because I didn't bother converting them. We'll have something for A3. And then for the average value, 0.004. I'll do 395. So this will be our kind of final value for A, for our constant. That'll be, and we probably want to write this in scientific notation because of this conversion factor. We're going to have an additional 10 to the minus 4. 10 to the 5th over 10 to the 9. That's 10 to the minus 4. And we already have a small number. So we have like 3.95 times 10 to the minus 3. So it's going to be kind of close numerically, just by that 1.01 factor. That's not going to change it much. We're going to have like something around 10 to the minus 7th power. So yeah, I'd write that in scientific notation. And just to, I'll just write this number in scientific notation. So this is 3.9 times 10 to the minus 3. So I'm going to do, okay, 3.9, I'm going to do this dot times, and then we have 10 to the minus 3rd. So again, in scientific notation, you can write things that way. Definitely, we're going to want to do that for the actual A once we convert it to these units, because, well, we should have something around 10 to the minus 7 as our exponent. Okay, so I think that'll be it for this video, and I'll have written instructions on what to do for the actual lab, which we pretty much did the first part. I think I'm going to have something else where maybe we'll change like the number of molecules and keep the temperature fixed. So we'll do something like that as well. And I've written, description for that as well. But that'll be it for this.